Welcome back to EasySpin Academy 2020. This is session 18, and on day 3 we're going to look at some high order spin operators, at trajectory-based EPR simulations, and the glance behind the scenes of EasySpin. So first, one of the requested topics was the simulation of high spin spectra, combined with requests about how to simulate lanthanides and actinides where there's no clean spin quantum number or orbital angular momentum number. And for both of these cases, it might be useful to know about high order spin operators that are available in EasySpin. So let's start out clearing everything, and we're gonna now simulate a terbium 4+ system, which is a spin 7/2, and it has a G value of 2.0136. Now, for these large spin systems, the high spin that don't just have a small zero field splitting like gadolinium or manganese, we have to include some higher order spin operators. And these include the spin operator to orders higher than squared in the spin Hamiltonian. So let's look at the documentation briefly. In the documentation under basics, there's the reference for the spin system. And if you go down to spin system parameters, you will see there is a selection of all the various terms you can include in the spin Hamiltonian. And one of them says higher order operators. Let's go there. These higher order operators are defined in fields that are called B1, B2, B3, B4, and so on. And the number indicates the power of the spin operator. So B6, for example, will include S raised to the power of 6 in the Hamiltonian. There is also a reference of the mathematics. These operators are called extended Stevens operators. And if you click on the reference here, it will take you to the actual math. This is a very general formulation for a spin Hamiltonian. It just involves a sum over these types of Stevens operators, where the second order is corresponding to the zero field splitting, but then there's also fourth order and sixth order, and some of the equations are written out here. These are operators, when people simulate these high spin spectra, these are often the operators and the coefficients they cite in the literature. So how does it work? I've prepared, I copied some constants over from literature. We don't have to think about these in detail here. The key point is now how these operators are defined, and I'm copying this as well. So first we define the fourth order terms, which basically mean S to the fourth, and that is given in the field called B4. This field has a total of 9 entries. And basically the order of these entries is the following. It's 4-4, 4-3, 4-2, 4-1, 4-0, and so on, all the way down to 4-4. These higher order operators are similar to angular momentum operators, so you have two indices. The first index is the exponent in the used in the S operator, which is 4 here, and the second index runs from plus to minus of the first index, basically in this case going from +4 to -4. And from literature we found that we have a non-zero number for the 4-4 operator parameter and one for the 4-0 operator parameter. The same applies for the sixth order term. That collects various terms that have S to the 6 in them. And in this particular example, there's only 2 non-zero 6th order terms, which is the B6-4 and the B6-0. Again, it starts at 6-6, 6-5, 6-4, 6-3, 6-2, 6-1, and so on. Now we can plot the levels using the function levels plot introduced earlier today. For this terbium system, we're going to put the field along the z-axis of the molecule, and we're going to give a field range from 0 to 2500 millitesla. If we press Ctrl Enter, run this, we get the energy level diagram, and it does look complicated. We have at zero field we have 3 different degenerate manifolds of states. that upon increasing the field start crisscrossing quite substantially. Now, let's actually zoom into some of these crossings and see whether they're actual crossings or not. For this, I'm going to define a much finer granular field axis using linspace from 0 to 2,500, maybe there's a 10,000 points. And instead of just a field range, I'm going to feed levels plot with the full high resolution field vector. Okay, and so now if you look at that, we can see that these crossings are actually very sharp. No matter, if you zoom in too closely, you will see the resolution of the field axis, and you kind of see there's kinks in the curves. Now, what if we change the direction, the field direction? We can go to X, and similar, we'll still have crossings that are happening, but we can go using defined theta angles. We can go to a slight off axis, let's say 0, 0, and multiply this by pi over 180 so we can enter degrees. Let's go 1 or 2 degrees off. Right, and there were minimal changes, but if we zoom in now, we can see that these what looked like crossings are now actually anti-crossings. So just a 2-degree change in the alignment of this system converts a crossing into an anti-crossing. This here that looks like a line crossing, if you zoom in fine enough, is actually an anti-crossing. So in a way, it's useful to think about these level crossings as really infinitely sharp anti-crossings, where the lines really come infinitely close together. And as soon as you have any little bit of misalignment, these crossings become actual anti-crossings. Actually, let's use the other levels function. So levels plots the energy levels. But levels by itself, if you feed it with the same inputs, I'm going to copy them down here, returns the energy level, the calculated energy level. So for each field value that we entered, it will give us all the energy levels of the spin system. And we can plot them ourselves. Just saying plot B0 for the field axis and E for the energy values. And if I run this, MATLAB colors each of the energy levels in a different color, so we can actually follow how EasySpin treats them. And as you can see, EasySpin never crosses over the energy levels. They're always numbered from the bottom to the top. Right? So for example, the light orange is level number 3 in high field, and it's level number 3 at low field. And even if there's apparent crossings, it still keeps level 3 from the bottom as the orange one. Right? Even this crossing here, I think, might be an anti-crossing. Yeah, the resolution is not quite sufficient. Let's increase the resolution. Let's do 100,000 points. That will now take a second or two to evaluate, but now we've got it. And if you zoom in again into this crossing, you will see it's actually an anti-crossing as a result of these 2-degree misalignments. So this just is an example of how to use these high-order spin operators to generate these more complicated energy level situations that occur for further down the periodic table. And this terbium example is actually among the official EasySpin examples. I'm going to actually show you what it does. It's funny. It's a little animation that I wrote a while back that shows how the resonances on this energy level diagram move as we change the microwave frequency. So this example is showing an animation and is increasing the microwave frequency and just highlighting where the transitions are. Pressing Control Enter to run it now. And as you can see now, you can see red vertical lines which indicate where resonances are at the specific microwave frequency, and it's being increased. The dependence is very complicated. Sometimes there is level pairs that have 2 resonances, and these are so-called looping transitions. And only once the microwave quantum gets really large relative to the zero field splitting, then the number of resonances becomes smaller and more intuitive. But as you can see, even at these fields, even at these frequencies, there's still a ton of possible transitions. And only now, with a large microwave quantum, the situation is getting slightly more understandable. So these are some things you can do with EasySpin with about 50 or 60 lines of code. So that was a brief example of how to specify high order operators and to simulate high spin system in a more general fashion. If you have to go beyond zero of the usual zero field splitting tensor of D. One more pretty large feature of EasySpin I want to introduce you to is trajectory-based simulations. For this, we have a function called cardamom, which was developed by Peter Martin, who was a graduate student at the University of Minnesota. And he collaborated with me to incorporate this into EasySpin. So cardamom and a series of other functions allow you to generate stochastic trajectories or load molecular dynamics trajectories, and then use those in combination with some spin dynamics calculation to actually simulate an EPR spectrum. So first, let me show you how to generate a stochastic trajectory. What is that actually? This is used for simulating emotional EPR spectrums, for example, for a nitroxide in solution or attached to a protein. If it's not frozen, the nitroxide tumbles around rotationally, and that will affect its EPR spectrum because an EPR spectrum of a nitroxide is anisotropic, right? A different orientation of the nitroxide will generate a different EPR spectrum. So now, if you imagine that the nitroxide is tumbling while you measure the EPR spectrum, you can kind of, it's kind of clear that it will have an effect on the spectral line shape. Yesterday, we talked about slow motion CW EPR spectrum, which is exactly this regime where the tumbling affects the shape of the EPR spectrum. And yesterday's function was called Chili, and the Chili function uses a dedicated theory to model this tumbling in a generic Brownian diffusion way. It does not do a time domain calculation like we're doing now. Cardamom is way more general. It can take as input any type of trajectory you come up with for this type of rotations. And one auxiliary function allows you actually to generate some stochastic trajectories. Let's do that. So we're going to set a spin system correlation time. Actually, we don't need a spin system. We just need a correlation time. Let's say 15 nanoseconds. So the unit for t-core in this, just like for the spin system, is seconds. Then we call the function stochtraj for stochastic trajectory. Diffusion, basically telling EasySpin to provide us with a rotational stochastic trajectory that represents some sort of Brownian diffusion, rotational diffusion of the molecule. And we just feed it the correlation time. And what it will return a time axis and for each time point, a rotation matrix. So let's call this an R trajectory, R traj. So T is the time axis, and R traj is a trajectory of rotation matrix, of the rotation matrix. Because each orientation of the nitroxide is uniquely represented by a full rotation matrix. And so if the orientation of the nitroxide changes, the rotation matrix changes. And if you have a series of rotation matrices as a function of time, we've completely represented this rotational tumbling. So this runs really quickly. So we can actually, let's try to plot it. We have to do some technical array rearrangement here with a squeeze function. We're gonna extract the 3-3 element. So any rotation matrix is 3 by 3, and we're gonna extract the third element. Actually, before we do that, let's just run the code and look at what happened. There's an error. Let's see why the error happened. I think stochtraj does expect a spin system as an input because it can take more spin system parameters than just the correlation time. Okay, let's run it. That still doesn't work. This is t-core stoch diffusion. I have to remove this here. Voila. there we go. Okay, so it's been calculated. And if you look over at the workspace, our traj is now a 3 by 3 by 2000 three-dimensional array. So it's kind of a long kind of block of matrices, of rotation matrices, all stacked next to each other on 2000 of them, each corresponding to a different time point. We could now plot, let's say, one of those 3 by 3 elements and see its time dependence. And that's what I've started doing here with writing out RZZ. RZZ is capturing the 3-3 element. The 3-3 element is capturing all the time points, and we have to do a squeeze to eliminate some leading dimensions that are singleton now. So let's plot this as in I think microseconds and RZZ and see how it looks like. And as you can see, this looks completely random, and in fact that's the goal. You got a rotational trajectory, so each rotation matrix element is completely random. So this way you can generate a stochastic trajectory that's directly built into EasySpin. On the other hand, you can just load a molecular dynamics trajectory. And for this, use the function mdload. So you might have set up your protein with a spin label and have done a molecular dynamics simulation. You can import with mdload your output file from the MD simulation, and mdload will automatically identify the nitroxide and just disregard everything else, just pick out the nitroxide frames and convert them to a rotational trajectory like StokeTraj has done before. It works with charm and with NAMD. And let's briefly look at the documentation here to show you where that is. We've got a cardamom documentation, but you can also find this by category or even under alphabetical. So mdload, it's under mdload. So this shows you what you have to provide. You have to provide, of course, a trajectory file and a topology of information. So 2 files are needed. And mdload, once you provide those 2 files, you can also customize the residue name and the segment name where your nitroxide is, and you can then mdload that into MATLAB for later use with cardamom for simulating a trajectory. So once you have a stochastic trajectory or you have this molecular dynamics trajectory, you can then go ahead, do the spin dynamics and simulate the EPR spectrum. And I'll show you that briefly here. We're going to use a stochastic trajectory. I'm not using a molecular dynamics trajectory because those output files are really large and I did not want to include those in the zip file for this workshop, not to tax your download too much. But there is an example on the EasySpin, in the actual EasySpin examples, where you can see how the molecular dynamics files are loaded. Okay, let's start out, clearing everything up. Let's define a spin system, which I'm going to just copy over here. It is a nitroxide radical, so nothing new here. I'm using millitesla to megahertz to convert millitesla hyperfine values to actual, these are in Gauss actually, in Gauss, divide by 10 to give millitesla, and then use this function millitesla to megahertz to get the hyperfine coupling in megahertz. Correlation time of 15 nanoseconds, and some additional broadening, or Lorentzian broadening, due to some other dynamic mechanisms that are not rotational. Let's take an experiment of 9.4 gigahertz, so expand. And now let's write out the parameters needed for cardamom, which is the function that simulates the EPR spectrum from the trajectories. First of all, we need a diffusion, specifies a diffusion model. We're not going to load MD, we're just going to make a diffusion model. We're going to average over 200 trajectories to get a smooth spectrum, or relatively smooth. And then we finally have to specify how the spin and spatial dynamics should be solved or integrated. So it should propagate each spin dynamics in a 1 nanosecond step size, and the spatial dynamics, which is the tumbling of the nitroxide, also on a 1 nanosecond time scale. So what cardamom is going to do is going to calculate for every 1 nanosecond where the nitroxide is and which direction the spin on the nitroxide is pointing. And we're going to do this for 230 time steps, so we're going to get about 230 nanoseconds worth of a trajectory. And this is a trajectory that simulates the response of this nitroxide to a 90-degree pulse. It's basically simulating an FID. And then if you take the Fourier transform of that FID, we actually get the full nitroxide spectrum. Okay, so now let's simulate this with cardamom. Let's call this B1 spec 1 equals cardamom. We feed it the SPIS system, the experiment, the parameters. This is now different from all the other functions, the trajectory parameters, and the options. Any simulation options we might have. Let's put in options verbosity equals 1. This tells us just print information to the command window. This is available in all of the EasySpin functions. Okay, and since we're basically simulating a kind of stochastic tumbling of the nitroxide, we should have a situation that's can be also modeled with chili. And in order to do that, we also simulate the chili spectrum. So B2 spec 2 equals chili, and it's just cis exp. And we should probably, not sure, those cardamom is intensity calibrated. So let's just do that. Spec 1, just divide that by maximum of spec 1 and do the same thing for spec 2. And finally, we're just going to plot those two in the same plot. B1 spec 1, B2 spec 2. Now let's clear the command window and run this code. Hopefully I didn't make any typos. Yeah, now you can see the cardamom simulation is running. It is now looping over 100 orientations. It's doing 230 steps at 1 nanoseconds, and the command window shows it will take another 25 seconds to complete. Trajectory simulations take a lot of time, and chili is a lot faster. So if you have just simple Brownian diffusion, use chili by all means. But if you have a molecular dynamics calculations, you want to know what the PR spectrum is based on that MD simulation, load the data with MD load and then feed them into cardamom. Okay, here is the result. Let's type axis tight so you can see a little better. In red, we have the chili simulation, which is very smooth. And in blue, we have the cardamom simulation based on stochastic trajectories. And you see those spectra coincide really well, meaning that those two theories give the same spectrum for this type of diffusion. You can see that the cardamom simulation is a little grainy. We didn't do enough orientational averaging to completely smooth it out. It will probably take another factor of 3 or 4 longer to get it really smooth. But for the purpose of this workshop, it's probably sufficient to just show you it this way, how it works. Okay, so that was the last big simulation function that's available in EasySpin that I haven't talked about. Kind of to summarize, you have a series of simulation capabilities. We have pepper for solid state. We have chili for slow motion spectra, also with cardamom for trajectory-based slow motion spectra. We've got garlic for the isotropic limit for really, really small molecules in fluid solutions. We've got salt for Ender simulations. We've got saffron for pulse EPR simulations combined with Spidian if you want to get a little more advanced into spin physics. We have curry for doing magnetometry. And I think that's all of them. Let's go look back on the documentation. Yes, here they are. Garlic, chili, cardamom, pepper, salt, saffron, Spidian, curry. Remind you about block steady, which is the function that simulates rapid scan CWPR raw signals. Pulse to make shape pulses. And then, of course, probably the most used EasySpin function is ESFit. That allows you to fit spectra from provided by any of the other simulation functions. All right, so that kind of concludes the overview of the features of EasySpin. It's been a long 3 days, and I've been able to poke into every corner of EasySpin, but unfortunately not with great depth. So please just consult the documentation and in particular the examples if you want to learn more. In this last few minutes before we go to the Q&A session, I would like you to show how we do EasySpin in the back. So EasySpin is fully open source and free. So the source code is available on the web. What you need to do to get there is you go to github.com/stollab/EasySpin. Here is the URL. And if you go there, this is GitHub hosts open source and allows version control. You see the entire source code of EasySpin, including the documentation source files, also build scripts, and very importantly, a lot of tests. So EasySpin right now has about 800 tests if this all loads up. Yeah, this all loads up. And if you scroll through, this amazing long list of tests. And before an EasySpin version gets released, all these tests are run and they have to pass. Actually, let me start a test run. For this, I will need to go into the folder where my tests are and then just make sure what EasySpin version we're using right now by typing EasySpin. I'm using the version that you are using. That's the latest published development version for 6.0. And now we're going to just run all the tests so you can see how this works. This full test run will take about 10 to 15 minutes. It just goes through alphabetically through every EasySpin function and runs calculations and compares them to previous calculations or to explicit values. For example, it even checks the Planck constant to make sure the Planck constant is still what it needs to be. Right now you see here Boltzmann _value. That's a test to make sure when you type in Boltzmann, Boltz-M, you actually get the Boltzmann constant back. So it's a very simple test, but there's more complicated tests. I think it does about 100 different solid state EPR simulations to make sure, when we mess with the code, we don't screw up anything and break previously working code. Without these tests, EasySpin development would be impossible because these are tens of thousands of lines. And if you change a line here, it could have unintended consequences for like a specific application case. And only by having automated testing all the time, we're able to make sure EasySpin has all these bugs get squashed and stay squashed. And if you report a bug, we'll fix it. We even add a test to check whether this bug is reintroduced or not. Okay, right now it's doing cardamom tests, and cardamom is a slow function, so these cardamom tests take a while. So that's a brief overview of testing. Let's go back to the GitHub repo. If you're interested in looking at the source code, you can just browse on this website. For example, you can go to the EasySpin subfolder and look at the SOP function. SOP, where is it? SOP. And it will show you the code for the actual SOP function, which is 380 lines. You can also download the source code to your computer by just cloning, by clicking on the green button here, and then you can just download a zip file or clone it locally, and then you can modify EasySpin. So we do encourage that to do, but please, for your research, we recommend not using any locally modified EasySpin code because for reproducibility, that is a big challenge. If you use an official EasySpin releases are always available. You can click here on these releases button, and on GitHub you can basically go back to any release that's been published previously, and GitHub still has the snapshot of the source code for that particular version. So other scientists can go here and reproduce your analysis that you've published. If you use your own modified versions, then that is not possible unless you provide the full source code as a zip file in the SI. If you have suggestions for modifications, please let us know here on GitHub. If you click on this button, Issues, there you can submit any suggestions or bug reports that you might have, and we will take care of them. And as you can see, we have right now 46 open issues and that we're slowly working through. And many of them are new features we're planning to incorporate for version 6.0. And version 6.0 is a milestone that is shown here. And if you click on it, it will list it'll show you that there's 24 open issues that we still need to finish before we hit this milestone and we can publish version 6.0. EasySpin is automatically packaged and released. So if I on GitHub tag a new version, we've set up build scripts and a build server that automatically runs the test, packages everything up, and publishes it on the website. So if you find a bug, tell us about it. We can fix it and turn this around. As soon as the bug is fixed, it probably takes 15 minutes to push a new version out. It's all automated at this point. So let's see where the tests are right now. We're still in the cardamom tests. I should mention that although it was only me that talked throughout this workshop, there's actually a series of contributors that have contributed to EasySpin over time. And I want to give them a shout out because their contributions are really important. So first, Peter Martin, formerly at the University of Minnesota for the trajectory-based EPR simulations and the interface to MD. Claudia Teit wrote the pulse shaping function, also some mixer and transmitter linearity function, which we haven't talked about. Stefan Pribitzer did all the Spidian work, so the advanced pulse EPR simulations, as well as the software project infrastructure with the build system. Jeremy Lehner implemented the general stochastic Liouville solver for Chile. Joscha Nerkorn did magnetometry and frequency domain simulations. And Matt Krzyaniak, the ad blocker needs to update. Matt Krzyaniak did data import for SpecMan, which some of you might be using. Andrew Hope made the steady state solutions for Bloch equations. And I wrote some of the rest. So if you want to contribute, please go to GitHub, clone the repository, and maybe submit a pull request. For those who are not coders among the audience, if you have feedback, problems, or need some help, please go to the EasySpin forum at easyspin.org/forum, and there's 4 forums there, and the most important one is just a general forum where you can post your question, and somebody will hopefully answer it there. Okay, so what's the future of EasySpin? That was also one question. Well, the future of EasySpin looks like it's stable. We've got a good software infrastructure in place that kind of minimizes our effort of maintaining it. It's well tested. We're gonna build out features, and for EasySpin 6.0, the 2 most important things that still need to be done is reworking ESFit completely. You guys already have seen some aspects of that. One is that ESFit will only accept function handles as the first input argument, but the entire input syntax will change, the GUI will change, and we'll introduce things like calculating parameter uncertainties. So stay tuned for that. So that's one big change that will come for EasySpin 6.0. And the second big change is a rework of how the frames are organized. Because there is some experimental situations that cannot be simulated right now. For example, if you have an oriented film that's on a glass slide in your EPR tube with some oriented paramagnetic centers, and you put that in your EPR spectrometer, you get a partially ordered EPR spectrum. Now, if you turn that sample tube, the spectrum will change because you're changing the orientation of the film. This can currently not be cleanly simulated with EasySpin. You can hack it with abusing some of the frames that are not intended for what you're using them for. But our goal is to make it really, really clean and easy for you to just rotate a sample and see whether the EPR spectrum changes. Our goal is also to let you turn a sample for a powder spectrum and observe that the spectrum is not changing. So that's the second big thing that will come in the future. And we hope that in the future we'll have more contributors. So if there's anybody of you out there who's good at MATLAB and knows something about EPR or just wants to contribute improving the documentation, all these contributions are really welcome. Because EasySpin right now, what it suffers from is a lack of manpower and women power to develop it further. Yeah, this brings me to the end of this session. It's about 10:26. We'll have, in about 4 minutes, we'll start a Q&A session. And then in about 34 minutes, we will start the happy hour. One thing to mention here at the end of this session is that Stefan has now posted an exit survey for this workshop, and you can find it on the website, easyspin.org. Then you go to the Academy website, and now there's a red button that will bring up a Google survey, a Google form that we ask you to fill out. It just asks you what you thought about this EasySpin Academy, what you think went well, and in particular also things you think we might, that are worthwhile improving if you run this again. So please go to that website and fill it out. Either you can start, I think you can start now, and I'll see you in a few minutes back at the Q&A session.